Good evening. My name is Keelan Wright, and today we'll be going over concavity and inflection. This is part 3 of an originally 2-part series. It ran a little bit longer than I thought it was going to, so I had to break it up into separate parts. So in the other first part and second part, we went over general notes for inflection and concavity, as well as 2 practice questions. On part 2, I didn't finish the last sketch of the second derivative of the function. So for reference, I'll go over that very quickly before I start the final question. So we had already solved for our critical points, and we had already solved for our inflection points. So what we did was we took this equation right here, of the second derivative, which was this part right here, this is the numerator. So we rewrote that as the second derivative is equal to 2x to the fourth plus 42x to the third over x to the seventh. That part comes from right here. We had done enough algebra to simplify it down to that. So what you want to do after this is you want to pull out an x cubed, and you can pull out an x cubed to basically further simplify the actual equation. By pulling out an x cubed, you're left with 2 times x plus 21 over x to the fourth, because x to the third divided by x to the seventh is x to the fourth. You can find your x-intercept by setting the equation, setting y equal to 0, which will leave you with negative 21, 0 as your ordered pair. The y-intercept is undefined because there's a restriction on the domain that x cannot be equal to 0. Then we want to look at the end behavior as x approaches positive infinity, negative infinity, 0 from the right, and 0 from the left. As x approaches positive infinity, we will have a large number over an even larger number, which means that this will get smaller as x gets larger, which means it approaches 0 from above the x-axis, because this will be have a positive sign. As it approaches negative infinity, you will have a negative number in the numerator over a very, very large positive number, which will mean it will approach 0 from below the x-axis. As it approaches 0 from the right and 0 from the left, both of them will approach positive infinity, namely because this one will be positive in the numerator and positive in the denominator for 0 from the right, because it's still a positive number, and this is going to be cubed. So this will be a very small number of a very large number, which will make this grow very fast. And then you'll have a negative number to an even power, which will also make it positive. And because the negative number is negligible, it's not big enough to make the numerator negative. So because of that, they'll both approach positive infinity. And using that, this is the graph we got. So we took all 3 of our graphs, the graph of the first function, the graph of the first derivative, and the graph of the second derivative, to go ahead and find our points, our intervals for increasing, decreasing, concave up, and concave down, and these are those intervals. Now, we're going to go ahead and we're going to do the final question. So for the final question, we have y is equal to 5 to the power of x minus 3x. Now, this type of question looks simple, but it's actually not as simple as it looks. And that's because a lot of people assume that the derivative of 5 to the x is just 5 to the x. It's actually not. The derivative of e to the x is equal to e to the x. So I understand the comparison, but this is not true. The derivative of 5 to the x is actually 5 to the x times the natural log of 5. I won't show it in this question, but basically the way you do that is you rewrite this as e to the x. So you rewrite 5 to the x as being equal to e to the natural log of 5, all of this to the x power. And then you can do chain rule and you can find the derivative of it. I'm not going to do that in this question. So in order to find the inflection point, I need to find the first derivative. So the first derivative with respect to with respect to x, will be equal to 5 to the x times the natural log of 5 minus 3, While I'm at it, I will also go ahead and calculate the second derivative. So the second derivative with respect to x will be equal to 5 to the x times 2 natural log of 5. And the way I like doing this is I just pull out the natural log of 5, and then I just take the derivative for what's in the parentheses, and I just keep the constant outside. Derivative of a number is 0, and then when I multiply it back out, you have a natural log of 5 times the natural log of 5, which is 2 natural log of 5. So for the first one over here, we want to find the critical point, so we'll set it equal to 0. So we'll say dy dx is equal to 0. So 0 will be equal to 5 to the x times natural log of 5 minus 3. Add 3 to both sides. 3 will be equal to 5 to the x times natural log of 5. Divide by natural log of 5. 5 to the x will be equal to 3 over the natural log of 5. Take the natural log of both sides. X times the natural log of 5 will be equal to 3 over the natural log of 5. Bringing the x down from the exponent is the entire point of taking the natural log of both sides. This is a property of logarithms. Basically, if you have something raised to the power of a variable, you can bring the variable down, or a number, and divide by natural log of 5 to get our answer. So our critical point will be at x is equal to 3 over the natural log of 5. All of that divided by the natural log of 5. For our inflection point, we set the second derivative equal to 0. So we're going to have 5 to the x times 2 natural log of 5 is equal to 0. Divide the 2 natural log 5 over. 5 to the x is equal to 0. Take the natural log of both sides. X times the natural log of 5 is equal to the natural log of 0. 0 is not within the domain of natural log functions, so this value is undefined, which means the inflection point does not exist. So next, what we want to do is we want to go ahead and we want to sketch the graphs of these functions to see how it behaves. So in order to do that, there's a couple of different ways you can sketch it, but we're just going to sketch each graph independently of the other one, and we're just going to go from there. So when I'm sketching the first function, what I'm going to want to do is, here we go. So I'm going to want to try to find the x-intercepts, the y-intercepts, and then I just want to look at the end behavior. So I'll be trying to find the end behavior as it approaches 0 from the left and 0 from the right, and positive and negative infinity if it's necessary. So what I'm going to do first is I'm going to find the x-intercepts. So I'll set, we know the x-intercept is when y is equal to 0. So we can say that 0 is equal to 5 to the x minus 3x. So we get 3x is equal to 5 to the x. We take the natural log of both sides. So we'll have natural log of 3 plus the natural log of x is equal to x times the natural log of 5. This is another property of logarithms, in case you're wondering. If they're being multiplied, that means the logarithms themselves are being added. And this actually can't be solved for because you have an x outside of the natural log and you have another x inside of the parentheses. So there is no x-intercept. So the x-intercept does not exist. Next, we can go ahead and look for the y-intercept. Well, we know the y-intercept is when x is equal to 0. Anything to the power of 0 is 1. So we have 1 minus 0. So our y-intercept is 0, 1. The next thing we want to do is we want to see the end behavior as x approaches positive infinity and negative infinity. We don't need to see the end behavior as x approaches 0 because we already have the y-intercept. So we actually already know that as x approaches 0 from the left and the right, it's just going to approach 1. So if we take a look at this, we can see that as x approaches a very, very big number, this number will be a very, very large number minus a not as large number. So this will actually approach positive infinity. As x approaches a very, very small number, this number will approach 0 because anything to a negative exponent is 1 over that number to the exponent, and this number will approach a very, very, very large positive number because it's a negative number times another negative number. So this will also approach positive infinity. Using that information, we can sketch our graph. No x-intercepts, one y-intercept at 0, 1, and it approaches positive infinity on both sides. Now, this looks like a parabola. It's not a parabola. It looks a lot like a parabola, but you have to remember this is also a rough sketch. Technically, this side grows to infinity faster than this side does, but for a first rough sketch, this is all you need. So that's the function, that's the graph of the first function. For the graph of its derivative, we know that dy dx is equal to 5 to the x times the natural log of 5 minus 3. So we can do the same thing we did before. We'd already solved for the x-intercept because we know the x-intercept is going to be 3 over natural log of 5. Let me try to write a little bit more straight here. 3 over the natural log of 5 divided by the natural log of 5. And then all of this is over the natural log of 5. So this number is actually going to be really, really small. And then once you subtract 3 off, let me use my pen, it'll be negative. So our x-intercept will be 3 natural log 5 over 5. Natural log of 5, 0. Our y-intercept does not exist on this one because if you look at it, we have, so our y-intercept is when x is equal to 0. So that would be 5 to the 0 is 1 times the natural log of 5. Excuse me, it does exist. So it's going to be 5 to the 0, which is 1 times the natural log of 5 minus 3. So it's basically 1. So our y-intercept is going to be 0, natural log of 5 minus 3. We can look at our end behavior as x approaches infinity, positive and negative infinity. We can see what y does. So as x approaches positive infinity, y will also approach positive infinity. We have a number raised to a very large number, which would be a very large number, times a smaller number, but it's a small number times a very, very big number, so it'll still be a big number, minus a very small number. So this will be positive infinity. If we look at what it does as it approaches negative infinity, we'll have 5 to a very large negative number, which will approach 0. So we'll have something that's basically 0 times something that's small, which will still basically be 0, and then minus 3. So this number will actually approach negative 3. With that information, we can go ahead and sketch our graph. So we have our x-intercept. This all comes out. This is something that's basically a really small. So this is around 0.6, and then you divide it again. So all this comes out to something along the lines of around 0.3, maybe 0.4. It doesn't matter, we know it's positive. That's the importance of it. So we know that's a positive number. This is around, this number is less than 1, so we can just say it's 0.6 minus 3. So all of this will come out to a negative number. That's just approximating. I don't need to do too much more than that because I know that this number is still going to be less than 1, so something less than 1 minus 3 will be negative. We know it approaches positive infinity on this side and negative 3, so I can just do this. So this is our graph of this first derivative. And then you can just say right here, we can just draw a line and say this is a horizontal asymptote at y equals negative 3. Because we know it's going to approach negative 3. So let's go ahead and sketch our graph of the second derivative. Hopefully this doesn't break on me anymore. Okay, so our second derivative is equal to 5 to the power of x times 2 natural log of 5. So what you want to do with this one is you still want to look for the x and y intercepts like how you did before. So if we look for the x-intercept, the x-intercept of this function is when y is equal to 0. So x-intercept doesn't exist. And it doesn't exist because basically you have 0 is equal to 5 to the x. We've run into the same issue we did before. The y-intercept is when x is equal to 0. So the y-intercept would just be 0 and 2 times the natural log of 5. Because anything to the power of 0 is 1, except for 0. We can look at the behavior as it approaches positive infinity and the behavior as it approaches negative infinity. So as y approaches a very large number, we can say, so 5 to a large number is a large number, times a not as big number will still be a large number. So that's positive infinity. And then we have 5 to a very large negative number. This will approach 0. And something that's approaching 0 times this number will also be a very, very small number. So in this case, we can just say that this will approach 0. It's 0, it's approaching 0 from above the x-axis. So we have a number that's basically 0 times a really small number, so that number will basically be 0, more or less. So with that information, we can go ahead and sketch our graph. So we have our y-intercept. We don't know what this value is exactly, but we know it's positive, so that can go about right here. And then it's going to approach 0 from the left, and it's going to go up to infinity from the right. So this is our graph. Label points, so this is 0, 2 times the natural log of 5. This was 0, 1. This point was 3 divided by the natural log of 5 divided by the natural log of 5, 0. Probably the longest one we've been writing out. And this one was 0 natural log of 5 minus 3. If you want the exact values, you can always feel free to use a calculator and get them. And all of these were rough first sketches. So this is the original function, the first derivative, and the second derivative. So with that, we can go and find our intervals of increasing and decreasing. So for our first one, let's put them side by side. We know that our function will be increasing when the derivative is positive. So if we take a look at this graph, it's positive from this value to infinity. So it's increasing from 3 over the natural log of 5 all over the natural log of 5 to infinity. Excuse me, we're using interval notation, so there's no brackets, it's only parentheses. So parentheses here and parentheses here. It's decreasing when the function is negative, so it will be decreasing from negative infinity all the way up to that value. So it will be decreasing from negative infinity to negative all of that number. I think you guys are getting the idea with this big negative number. I won't assign it a variable name because I only have to write it one more time. So it's decreasing from 3 over the natural log of 5 divided by the natural log of 5. And then we can look at concavity. Concave up is when the function is positive, and there actually is no inflection point, so it doesn't ever change. So this function is concave up over all real numbers. So it's concave up from negative infinity to positive infinity. And those are our intervals for these questions. So in closing, we went over a lot of different stuff, but namely the things that we went over was we started off with the notes that we actually had. So our notes just explain concavity as a whole. So we talked about critical points, inflection points, and then increasing, decreasing, and then what concave up and concave down looked like. We showed the general process for how you'd actually go about calculating those. Basically, if you were solving for x with the original function, you get the x-intercept. If you're solving for x with the first derivative, you get the critical points. If you're solving for x with the second derivative, you get the inflection points. And then we started looking at questions. So in each question, we were finding the critical points, the inflection points, if applicable, and the intervals of increasing, decreasing, concave up, and concave down. A lot of information, but that's the process that we're going for all the questions. And you can find them using a number line. I prefer to graph it, which is the entire point I graphed it for you guys, so you had a little bit more information. So we found the critical points, we found the second derivative, and found the inflection points. And then all these intervals we got by sketching these graphs. And we sketched the graphs by finding x and y intercepts and looking at end behavior as it approaches infinity, negative infinity, and 0. And this was the sketch of the second derivative for question 1. And then after that, we moved on to the second question. And when we were solving for the second question, we just went and we did the same process. The first question actually uses something called product rule. The second question uses something that's called quotient rule. And the third function uses something that's called the chain rule. So product rule and all of those are actually its own separate video. They're prerequisite skills, but this is how you go about solving for it. And then we went and we found the second derivative and we solved for that as well. And then these intervals of increasing and decreasing, again, we got by sketching the graph. So we took the graph here, and we sketched the graph of the first function, and then we went and we sketched the graph of the first derivative, and then we went and we sketched the graph of the second derivative, and after we did that, we tied all that back to get our intervals of increasing and decreasing. And then we moved on to the third question, and on the third question, we had to establish a notion that a number to a variable x is not just equal to the number raised to the variable x. It's actually equal to the number raised to the variable x times the natural log of that number. And the proof of that is actually its own separate chain rule. But that's just the way you go about actually solving for those. And then after we did that, we went and we sketched the various graphs for it. So we found the critical point, we determined that there is no inflection point, and then we sketched the graph for the original function, which although it looks like a parabola, it's not. We sketched the graph of the original function, we sketched the graph of the first derivative, and we sketched the graph of the second derivative. And then we took all that information and we went back and we solved for the intervals of increasing, the intervals of decreasing, the intervals of concave up, and the intervals of concave down. And by doing all of that, we managed to actually solve the problem as a whole. In case you're wondering what the second derivative graph looked like for question 2, here is the graph for question number 2. It looks very similar to the graph of the original question before you took any derivatives. They look very similar, but if you notice, their x values are a little bit different. They do look similar. The only one that's different is the first derivative. And that is an overview of inflection and concavity. Hope you guys learned something from the video. If you have any questions, you can leave them in the comments. If you have any math subjects, you can also leave those in the comments, and I'll get around to it eventually. This is calculus. I was just testing the waters with things since my last video was algebra. So I understand it's a pretty big jump since I jumped from algebra past pre-calc and trig all the way up to calculus. But that is everything I have for today. If you want to try the questions in your own free time, then here are the questions I did. Remember, the first one uses product rule, the second one uses quotient rule, and the third one uses chain rule. The second one really uses quotient and chain rule, but you can go ahead and try these in your free time. Thanks for watching, guys, and I hope you have a nice day.